if you think you can go through this by skipping steps, I just don't go down that road. It's very systematic. Okay? If you do it step by step, you will have success every time. Okay, so we know how to balance redox reactions using half reactions. This works good in acidic conditions and for simple half reactions, but we can also use oxidation numbers to balance them. And so we use it as a method when we need to know how many electrons are transferred per atom, per molecule, per reaction. Okay? So there are 5 steps that we go through in this process, and we label them as such. Step 1, you have to go through and do all of the oxidation numbers, and then you have to identify which ones are reducing and which ones are oxidizing, which ones we have the change in. The next step is determine the number of electrons transferred per atom. So this is key, this per atom piece right here. Per atom, by calculating the difference between the final oxidation number and the initial oxidation number. So if I start out at 0 and I go to +3, then my final number is 3. If I find I start at 0 and I go to -3, my final number is, like, my oxidation change is -3. We need to know those pieces, okay? Once we do that, then we look at the number of electrons transferred per molecule or per the reactant. So say we're looking at aluminum and we do a single replacement reaction and we end up with aluminum 3 oxide. So we are going from 0 to 3 plus. And we're looking at aluminum oxide. First, we're looking at just the change of aluminum, and then we look at the whole compound of aluminum oxide, the whole reactant. Okay? So this is per molecule. And then step 4, you balance the total number of electrons transferred by finding the lowest common multiple. So just like we did in half reactions, if one reaction had 2 electrons and the other reaction had 3, we simply switched and multiplied the top one by 3 and the bottom one by 2 to come up with an equivalent of 6 electrons in each line. Okay, same idea. And then step 5, you take those numbers and you go back and you balance your question. Let's look. It says use the oxidation numbers to balance this equation here. So the first step says figure out the oxidation numbers. What's the oxidation number of hydrogen? What's the oxidation number of hydrogen? +1. What's the oxidation number of sulfur? -2. What's the oxidation number of oxygen? What about the oxidation of oxygen here? -2. Oxidation number of sulfur. Oxidation number of oxygen here. And of hydrogen. +1. Okay? This is something I truly believe you are all very good at. Any questions to how we got the +4 for sulfur? No? Good. Step 2, this is what we call per atom. So here we see that we have to go the number of electrons final minus the initial. So here we start out at hydrogen doesn't change, it's +1 to +1. Oxygen doesn't change, oxygen changes, sorry. Sulfur changes -2 to +4. So here we're looking at +4 minus -2. So how many electrons is that per sulfur? Plus or minus? +6 electron per sulfur. Okay? Oxygen goes from 0 to -2. So -2 minus 0, what do we get? -2 electrons per oxygen atom. Okay? Thumbs up, thumbs sideways, thumbs down. Okay? Step 3 is per molecule. And if you're writing a test and you come up and you ask me for help, I physically do this. I don't skip steps. So per molecule, we're looking at H2S. So I have +6 electrons. How many S molecules are in this compound? 1. 1 S. So +6 electrons in an H2S molecule. Let's look at this one. How many electrons, how many oxygens are in this molecule? 2. There's 2. I'm going to write oxygens here. There's 2 oxygens for a total of -4 electrons per oxygen compound, or per oxygen molecule. Okay? Step 4 says per reaction. So I have 6 electrons here and 4 electrons here. What's the lowest common number we can get to between the two of them? No, we don't go down, we go up. What's the common number I can multiply them to? 12. So I'm going to take my positive 6 electrons, I'm going to multiply them by 2 so that I can get 12 electrons here. These ones here, I'm going to take my -4 electrons, multiply them by 3 so that I can get 12 electrons here. 12 electrons, 12 electrons, which means that I'm balanced. So now what do? I take these two numbers here and I put them up into my equation. I have 2 here and I have 3 here. So then I go through step 5. Balance the remaining reaction. So I put 2 here and I put 3 here. I must put a 2 here so that I can satisfy my sulfurs. I have 4 hydrogens here, so I would put a 2 here to get my 4 hydrogens. I have a total of 6 oxygens now. 4 and 2 make 6. This is where Cameron Lund said, all right, balance this unbalanced reaction. Okay, first step is S8. S8, sulfur, elemental sulfur. Water, yeah, this is peroxide. This is water. This is peroxide. Okay, let's go through and let's do oxidation numbers. Hydrogen, sulfur, hydrogen, oxygen. No, there's hydrogen. Not that there's two of them there. Hydrogen in and of itself is only a +1. -1. That's that special rule for oxygens. Good catch, Declan. Sulfur, hydrogen, oxygen. Okay, so what's changing? Sulfur's changing and oxygen's changing. Okay, so step 2, this is per atom. So sulfur and oxygen. Sulfur goes from 0 to a -2, or final minus initial, sorry, goes from 0 to -2, which gives us 0 minus -2, 2 electrons per sulfur atom. Oxygen ends up being -2, and it started out being -1. So it ends up with -1 electrons per oxygen atom. Okay? Step 3, per molecule. We're going to take our 2 electrons. We're going to look at our hydrogen sulfide molecule. How many sulfurs are in there? 1. Multiplied by 1. It's 2 electrons per H2S reactant. Let's look at this one here for oxygen. I'm going to take my -1 electron. I'm going to multiply it by how many are in my molecule? 2. The reactants. We always look at the reactants. Okay, here I've got 2 electrons and 2 electrons. It's in a 1 to 1 ratio, right? So now what we need to do, I'm just going to write this little note. When we balance our coefficients, they need to be in a 1 to 1 ratio. If I go back here to the previous example, this is a 2 to 3 ratio. So that means no matter what we do, it's either going to be 2, 3, 4, 6, 6, 9. It's got to be in a 2 to 3 ratio. Okay? This one here, no matter what number we come up with, it has to be in a 1 to 1 ratio. No, but let's look. We have a skill set. We can balance without all of this work. How many sulfurs do I have here? So I have to put an 8 here. Because of this piece here, that means I'm going to put an 8 here. It's a 1 to 1. If I put 8 on hydrogen sulfide, I have to put 8 on peroxide. So I've got 16 hydrogens here and 16 hydrogens here. So I'm going to put a 16 here for 32. That also gives me my 16 oxygens. And now I'm balanced. And this is that time, and maybe not. You would have done 8 sulfur, so you would have put an 8 here. That would have been 16 hydrogens here. So you would have put 8 here. That would have been 8 oxygens. You would have put a 4 here. That would have only been 8 hydrogens. And you're like, well, that doesn't work. And then you would have had to have gone back and forth and back and forth and back and forth. This eliminates that back and forth piece. By the time you go back and forth, you're done this piece and you know that it's a 1-to-1. And when I look here, it's pretty obvious I have to have 8. And this says that these have to be the same. So it's just another tool to help you balance redox reactions. And every reaction that happens is a redox reaction. Every single replacement, every double replacement, every formation, every decomposition, any reaction that happens is a redox reaction. So we've just upped our knowledge game. Yes, actually, I think you got it right. One atom with 2 different oxidation numbers in the product end. I think that sounds right, Declan. Okay, it's possible for some atoms of one element to undergo oxidation and also undergo reduction. And we call it that disproportionation. We looked at it, but that's all we did was we looked at it. So we can look at something like this. So we got copper 1 oxide plus sulfuric acid gives us copper, metal, copper sulfate, and water. So let's just start. Oxidation numbers. Oxidation number of oxygen here. -2 copper. Copper is +1. Hydrogen here, +1. Oxygen, sulfur,
SO4 right there, the sulfuric acid.
yeah.
So why did you put the S and the O together for oxidation?
What?
Because you put the +1 for hydrogen.
Yeah.
So then where's
the negative? That's what we're figuring out. I don't know. Everybody's got a different answer. We need to come to a solid answer. Eight plus 2 plus is 10 plus.
No, but you gotta move it to the other side, so it would be 10.
I know. So what is sulfur?
It'd be 6, so it's 6.
Okay, let's look at sulfur. +1 times 2 is 2 plus. 4 times -2 is 8 minus. 8 minus +2 is, I did that wrong. 8 minus, we're solving for this, so we would call this one x. So we would have +2 plus x minus 8 is equal to 0. So x would be equal to 8 minus 2, which is plus 6. Okay? And that was a tough one. Copper is a solid. Copper here. Oxygen. Over here? What's the charge on sulfate? Yeah. So what's sulfur here? Hydrogen? Oxygen? Okay, what changed? Copper went from plus 1 to 0 and plus 1 to plus 2. This one here where it goes from 1 to 0, what happened? Okay. And when it went from 1 to 2? Okay. So we can say that copper 2O is oxidized to copper sulfate. And we can say that copper 2O is reduced when we go to copper as a solid. So we agree that this is a disproportionation reaction. We maybe need to bone up a little bit on our practice. But we did not bad. Okay. Well, now we can use that to balance an equation. It says, balance the following unbalanced equation for disproportionation in acidic solution or nitrous acid forming nitric acid, nitrogen monoxide, and water. So, okay, so that's what we get. We're going to start with some oxidation numbers, just so we know what's changing. Hydrogen, oxygen, nitrogen, hydrogen, oxygen, nitrogen, nitrogen. Or let's start with oxygen, sorry. Nitrogen, hydrogen, oxygen. What's changing? Whoops. So when it goes from plus 3 to plus 5, is it being oxidized or reduced? Oxidized. When it goes from plus 3 to plus 2, it's being reduced. So we're going to look at this reaction. That's going to be one reaction that we look at. It was done in an acidic situation. So how do we balance this half reaction out in an acidic situation? Okay. I did that. What else do we have to do? So I did the oxygens are balanced. Now what do I have to balance?
I gotta balance the equation.
Well, I gotta balance my hydrogens out.
So you put a 2 on the other one.
Would I? You add a hydrogen ion. I can't change this. Otherwise, I change the number of nitrogens, and I'd have to change the number of nitrogens here. We add a hydrogen. For every water, we add hydrogens, right? Okay, and I need to look at net charges. This is 0, this is 0, this is 0, this is plus 2. So what do I have to do? Where? On the product or reactant? 2 positive plus 2 electrons is going to give me 0. Okay, let's look at the other reaction. HNO2 gives me NO. So this is in acidic conditions. What do I do? Okay. Because this is 0, this is 0, this is 0, this is plus 1. So we need to add 1 negative. Now we can balance it out. What's my next step? Why, Declan? There you go. My what? I was just doing my total ions. So now I'm going to look. I have 1 water here, and I have 2 waters here. I'm going to cancel this one and take 1 away from here. I just didn't write them in. 2 electrons and 2 electrons. The whole point of doing that was to cancel electrons. Here I have 1 HNO2 and 2 HNO2, so I'm going to combine them. 3 HNO2s. And then I have 2 hydrogens on this side and 2 hydrogens on that side. So they're going to do what, Declan? Cancel. Which leaves me to have an HNO3 on this side and 2 NOs on this side. And the easiest way to check is just check your balances. 3 hydrogens, 1 hydrogen here. What did I do wrong? Over here. Thank you. See? Knew I did something wrong. So 3 hydrogens, 1, 3. 3 nitrogens, 1, 2. 6 oxygens, 3, 5, 6. Balanced.
Boom.
Boom. Mic drop. Okay? So this disproportionation is not any different than balancing half reactions. It's just that you take the same reactant in both half reactions. It is weird. Let's look at I was going to say it happens lots with chlorine. Well, here we go. Hypochlorite ions. Disproportionate to produce chlorine ions and chlorate ions, right? A balanced redox reaction for this disproportionation reaction. So it says ClO ions disproportionate to produce chlorine ions and chlorate ions. Oh, I see. I don't know why it's doing that. I can zoom in a little bit. Is that better? Okay. Okay, so oxygen is, chlorine is what? +1. Chlorine gas, oxygen, chloride, +5. So you're going to have -6.
Oh, for some reason I saw a C.
No, it's Cl. It's not carbon iodide, it's chloride. Okay, so we go from 1 to 0 here, and we go from 1 to 5 here. So ClO negative goes to Cl2 gas, and ClO negative goes to ClO3 negative. How are we going to do this? Does it tell us that it was in an acidic reaction? Does it tell us that it was in a basic reaction? So we're going to actually use the oxidation numbers. I know. Look at your happy, happy, joy, joy. You what? Oh, you crush my soul. Okay. What? Chem in college? Oh yeah, you do a lab every week. And you do a seminar and you do class. It is. It actually is way better than high school chemistry. I don't know. Okay. Oxidation numbers. So we went from in ClO minus, I'm just going to cross this off because we found out we couldn't do it that way. So ClO minus here. We're going to look at 0 minus +1. And what do we get? What did we do? Oh, hold the boat. I royally messed this up. Because I wrote the wrong things down even. Royally messed this up. Not even a little bit messed this up. Good. Declan, you're finally using pencil. It's only taken 4 years, but I finally got you using pencil. Yeah. Let's look at this question. Come back into focus. Let's read this more closely than what Mrs. Pierre did. Hypochlorite ions disproportionate to produce, which looks like what? Yeah. And I did chlorine. I just saw the word chlorine and just went straight to Cl2. Okay, let's do oxidation numbers again. This is -2, this is +1. This is -1. This is -2, and this is still +5. All right. Well, we did in the other one, but when we look here where well, it still would have worked. Still a decrease, but it was wrong. It was just wrong. It's a Friday, and it was just wrong. Okay. So if we were to look at ClO, if we still were to have had this decision, we would have looked at that and we would have said, does the question say that it was in acidic conditions? No. Does the reaction say that it was in basic conditions? No. We have no other piece of information. So then we get to do step 1. Let's look at ClO minus. Here we went from a +1 to a -1. So final minus initial, -1 minus 1 gives me what? You're having a my kind of day, Declan. Okay. And then in the second reaction, it's ClO minus to ClO3. So in a disproportionate reaction, we're going to have the same ion, chances are. It went from, on the final, at +5 to the initial was a +1. And so how many electrons do I have per atom? Remember, this is step 2. +4 electrons per chloride. Step 3 is per molecule. So when I look at this here, how many chloride ions do I have in this? So I'm going to take my -2 electrons, I'm going to multiply it by 1, I'm going to get 2 electrons for every chloride ion there. What about this chloride ion? How many chlorides are in this? 1. So I'm going to take 4 electrons. I'm going to multiply it by 1 so that I 4 electrons per chloride ion. Okay. Step 4 was per reaction. Well, I've got 2 and I've got 4. So what do I need to do? Two electrons times 2 and 4 electrons times 1. And I should end up with 4 electrons and 4 electrons here, which means that my coefficients are 2 to 1, except that 2 and 1, except that it's the same ion. This is 2 ClO minuses, and this is 1 ClO minus, which gives me a total of 3 ClO minuses, right? 2, and 1. Gives me Cl minus and ClO3 minus. This matches up, 3 oxygens, 3 oxygens. I got 3 chlorides here and 2 here. Well, why can't you see? Okay, I've got 3 oxygens here and 3 oxygens here. Put a 2 here. Now I balance. So the key part here is to remember that this is your coefficient, not the electrons here. This isn't 1 to 1. This is a 2 to 1, chlorite and chlorite. Okay? Let's go back to the first lesson, the balancing with oxidation numbers. And let's work on those practice questions, and then let's also work on these practice questions here. And then we're halfway through the unit.